planet.
Hi everyone, and welcome to yet another
The Earth is Flat on Planet Pluto,
an online cosmic talk show about astronomy, science, and other stuff, where the guests are the clear highlight and where you can ask any questions and also participate by using the chat on the side on YouTube. Now, every Wednesday at 5:30 p.m. UK time, we have been bringing you a cosmic topic and amazing guests who share their passion for science and space. This is already the 7th episode of the English version, but just like in all others, things can and will definitely go wrong. I must stress that this is core to the scientific method. Like blowing things up, this is how we learn. Because when things work perfectly, we also never learn anything at all. Now, during June and July, I have been your host as we attempted to bring you lots of astronomy, science experiences, the human side of looking up, and also a lot of fully random but hopefully fun stuff. My name is David Sobral. I'm an astronomer and a scientist. And just like everyone else on this amazing yet insignificant planet, I'm 10% made of cosmos and 90% made of stars, which formed billions of years ago. Over the past decades, we have collectively, as humankind, looked up like never before, mapping the universe in space and time and constructing the most accurate and meaningful 3D maps of the universe. Such surveys and the data gathered by them allow us to not only explore galaxies as if we are archaeologists like Indiana Jones in space or galactic archaeologists, but also to understand the nature of the universe as a whole and specifically its mysterious components, dark matter and dark energy. They also allow us to see that there are faint components of light around galaxies, which signal that many had a violent past, resulting from mergers of galaxies, but also revealing populations of really old clusters of stars that we call globular clusters. Now, today's guests will tell us all about galaxy archaeology, the amazing achievements of recent surveys, including the recently released 3D map of the universe, which is the largest ever obtained, but also about galaxy mergers and even globular clusters. Remember, of course, that you can directly participate and ask questions by using the chat on this side, and the voice from beyond will read your questions to our amazing guests, which will answer. For now, though, please welcome our amazing guests for today, Rita Tojeiro from St. Andrews University, David Orion and Emma, both from Lancaster University. Thank you so much for coming into the show. I hope you're all doing well and adapting to this new normal. So Rita, I'll start with you. And just for those of you, watching that don't know you, you did a PhD at the University of Edinburgh, and you were a postdoctoral fellow at Portsmouth before moving to St. Andrews, where you got a prestigious STFC fellowship. You have been also a lecturer there, and you're currently a reader. And I would highlight that you've also received the L'Oréal UNESCO Fellowship in 2015 for your brilliant and inspiring work. You have been heavily involved in the incredibly successful SDSS surveys, different versions, along with surveys like Vipers, Gamma, and DESI. And you are a co-author in many papers that have been cited more than 1,000 times each. Your work focuses on exploring large spectroscopic galaxy redshift surveys, which collect spectra for millions of galaxies in the near and distant universe. You then use those data to learn both how galaxies themselves have evolved, but also to understand the content, geometry, and expansion history of the universe. And just this week, a team you are part of released the largest and best 3D map of the entire universe. So first of all, thank you so much for being on the show. And to start with, could you tell us a little bit more about this amazing 3D map that was just released?
Sure. So thank you for the introduction. That is
a bit overwhelming, really. But that was brilliant. So yeah, so it's funny because when you asked me to do the show, we didn't plan this, right? I looked at the dates and we chose a date that we could all make it. But it also happens to be 2 days after this map was released. And the beautiful thing about this map is that it's the culmination of over 20 years of work, hundreds of people, countless hours of telescope time to build this absolutely stunning and full packed of information three-dimensional map of galaxies. So what we have here, and what you're seeing on your screens right now, is just a zoom out of that map. And so effectively what it is detailed three-dimensional positions of about 2 to 3 million extragalactic objects. And what they allow us to do is to find out where stuff is in the universe, or at least the stuff we can see, which I think we'll probably talk about is not necessarily all that there is to find out about the universe. But it is the largest, and it's not something that happened in 1, 2, 3, 5 years. It's a combination of 20 years of work.
So you already mentioned that this contains about something like 2 to 3 million galaxies. That's a lot. But how is it obtained? I mean, it took 20 years. What kind of processes did you have to go through?
Yeah, so you can think of it as a two-stage process, okay? And the first thing you do is you take a photograph of the sky, and you don't want just a photograph of a small patch of the sky. You want to cover as much of the sky as you can. So for the first 10 years of the survey, we basically just very slowly but surely took photographs of the sky until we mapped about 10,000 square degrees of sky. That's about, a quarter of the full sky. And once you've taken this photograph, you can look at that photograph and you can find things that are extragalactic. So things that are not in our galaxy. Just by the shape and the color, you can sort of guess that they're not stars in our galaxy. But that's a two-dimensional map. Okay, it tells you, if you think of coordinates on Earth and latitude and longitude, you can have something equivalent on the sky, which is RA, right ascension and declination. But that's a two-dimensional map. It has 2 dimensions, an X and a Y, an up and a down. So what you really want to do first, turn that into a 3-dimensional map, you need to get a distance. And to get a distance, you can't do that with just a camera. You need to use a spectrograph. And so the second step of this map is to get a spectra, an optical spectra, which is a sort of signature of the light coming from each object. And from that, you can get a distance. And so, the first 10 years sort of focus on getting that 2-dimensional picture. And then we've been slowly building the distances to make what you see now, which is this beautiful 3-dimensional map.
And one thing that's often useful to know as well is what kind of telescope was used to do this? Because people hear about increasingly larger and larger and larger telescopes. Did it require like one of these gigantic telescopes or not really?
No, and this is the beautiful thing about this. This is a 2.5-meter telescope, which in modern terms is a very modest sized telescope. It sits up in New Mexico in the US, in Apache Point Observatory. And it really is the little telescope that could. It just doesn't stop, and it hasn't stopped for 20 years. And it's just large enough that it can gather enough light to make these maps. But we are really pushing it to the limit, and we have. And so I think the next generation of these maps is going to be done with a bigger telescope, 4-meter telescope. But yeah, you don't. It's our little 2.5-meter telescope that has really done us immensely proud.
And the other thing that's really important to know is for people watching, why do we need such large maps, such large volumes? What is this adding to our understanding?
So that's a really good question. And so if you step back 20 years, if you step back over 20 years when people were starting to plan SDSS, so there was this dream of making the survey that would be 30 times bigger than anything else. And at the time, there was sort of 2-3 main motivations. One of them is that the larger the volume, the better you can understand how galaxies are distributed spatially in the universe. And so that allows you to learn a little bit about the content of the universe and the expansion of the universe. But I think the main motivation was really that if you have large enough volumes, then you sample enough galaxies, you observe enough galaxies, so you can start to disentangle some really intricate behaviors and relationships between the properties of galaxies that you can't do with small volumes. And I think what's really nice is that one of the early motivations of Sloan is that if you observe lots and lots of galaxies, then you're more likely to find something you've never seen. You're more likely to find something unexpected, to learn something new. And that was part of the motivation for Sloan, 20 years ago. So yes, it's that three sort of fold motivation: is mapping the unknown, trying to disentangle intricate relationships between galaxies, and trying to map the universe in as large volume as we can to understand how matter is distributed.
And I think an important question for people seeing this video in press releases and on the news, when you look at it, and especially when you zoom out of it, I mean, why is the universe empty on this along some directions? Are there no galaxies there?
That's an excellent question. There are, but for as much as we've done, we've not yet mapped the full sky. So we've mapped a fraction of the sky, and so what you're seeing there, we mapped about a quarter of the sky, and so what you're seeing there is about a quarter of the full sphere. So it's not that there aren't any galaxies there, we just haven't pointed our telescope at them.
And the other thing that's really important is to kind of understand what you can gain from this. And specifically, one of the things you do in your research is to try to look at this mysterious components of the universe. So how can we learn about dark matter that we cannot see by mapping galaxies that we do see?
So to understand that, you need to first remind yourself that dark matter actually outnumbers normal baryonic matter by about 4 or 5 to 1. And dark matter, we call it dark matter because it doesn't shine. It only seems to interact via one of the 4 fundamental forces, and that's gravity, potentially the weak force, but gravity. So it doesn't have the mechanisms by which it shines, but it does react. It does interact gravitationally with other matter in the universe. And because it's so overpowering over baryonic matter, then it actually dominates how structure grows. It dominates, what little clumps of matter in the universe will grow faster and how they will grow. So dark matter dominates that growth. We can't see it. However, galaxies are gravitationally attracted to the dark matter, and so we say that they trace it. So the way that I like to think about this is, if you think about nighttime satellite imagery, when you look down and you see the lights on planet Earth, on the surface of the planet. If I asked you to sort of try to estimate how much land mass there was just by the lights, you could probably guess where most of the land mass was, because where there's light, there's land, because people live there. People don't live in the oceans. It's sort of the same with this. So you see the galaxies where there's dark matter, and so you can map the dark matter distribution by mapping the galaxies. It isn't perfect in the same way that there are parts of the Earth that actually have land mass, like deserts and large forests, and there's less light. It's not a perfect relationship, but it's good enough to really understand how much dark matter there is and how it sort of influences the growth of structure in the universe.
And the other kind of dark component of the universe, can these surveys also be used to somehow put constraints on this mysterious component we called dark energy?
They can. And so that is largely the motivation for this last iteration, for the last few years of SDSS. And so to understand that, you have to sort of, well, trust me, because I don't have time to explain this in too much detail. So there is a certain pattern in the distributions of galaxies that has sort of a fixed size, or it was a fixed size, a known size in the early universe. And as the universe expanded, so did that pattern in the same proportion, if you will. And we call that a standard ruler. Okay, it's kind of it's something that we know the actual size of in distribution of galaxies in the universe. So if you can map that at different distances from us, you can see how the size of this ruler has changed, and you can see how fast the universe has been expanding. But to do that, and this is going back to your earlier question, this pattern is really difficult to disentangle. So you need many galaxies. You know, we need millions of galaxies in order to really measure it, and then measure it as distance from you increases, or from Earth increases, and that's how we can map the acceleration of the universe. Well, you can map the expansion of the universe, which tells us the universe is accelerating, which then tells us of this mysterious component, which was chosen to name dark energy.
And we'll develop this a little bit more just in a few minutes. For now, I'd like to go to our other guest, David Orion. David, first of all, a happy birthday.
Thank you.
Live on YouTube. I'm sure everyone congratulating you. I got lots of presents. And just to introduce you, so you did your master's degree in Glasgow, right? Where you studied something a bit more local, if I'm not mistaken, right? So you're looking at the sun.
Yeah, I was looking at solar prominences and how they evolve.
Yeah, but fortunately, you developed some good taste. So you've moved to things which are a bit further away, other galaxies. So you started your PhD almost a year ago at Lancaster University, where you've been working with the brilliant Brooke Simmons and also within the Galaxy Zoo collaboration. And you're currently, I would say, a galactic archaeologist focusing on merging galaxies. First of all, for people who have no idea what are merging galaxies?
Well, merging galaxies are, I suppose, they're starting with like what a galaxy is. You know, it's a system of gas and stellar material and that kind of thing that has a really, you know, is very massive and has a very strong potential well and gravitational potential and stuff. Now, when a galaxy mergers are happening, we have two of these galaxies which have these massive potential wells, which get very, very close together, and we start to see those wells interacting, and we start to see, you know, distortions in the disks or perturbations in the gas and that kind of thing happening within each galaxy. Now, how much this affects either of the galaxies is very much dependent on, say, the mass ratio of your galaxy. So if you have a really massive galaxy just sitting on its own, not doing much, and then like a very low mass galaxy comes in, all that's really going to happen is that low mass galaxy is going to get obliterated by the larger one, and then probably get absorbed, or it's going to form into some kind of weird looking irregular galaxy or that kind of thing, or even be captured as a satellite. When you have the mass ratios get kind of similar, so we say we have a mass ratio of 1, which means that, you know, massive galaxy sitting by itself, another one comes in as a similar mass, then that's when you really start to get lots of kind of weird effects that are like, you know, what you're seeing here. That picture there is an example of the Antenna Galaxy, which we think was a merger of two roughly similar, very massive galaxies, and all they did was just totally annihilate each other. Less violent versions of that, you know, you get things like starbursts, or you get just like tidal features form. And like what a tidal feature is say, like a bridge between the galaxies form. Like the two disks come close enough together that they actually kind of interact with each other, and then material actually kind of begins to cross over between the two galaxies, and they sort of stick together as they go. But these bridges usually then like fall apart pretty quickly as the galaxies pass each other by. A more interesting, more relevant tidal feature would be, say, a tidal tail, where you get the galaxy, one of the galaxies will actually have material completely pulled out of it, which then extends round on this long arm from the main galaxy. And that was in one of the images that you showed just there as well. And a number of things can happen to this tidal tail, but I'm mainly interested in when it's still staying connected to the main galaxy.
I mean, an important question is, don't galaxies know that there's a pandemic ongoing, and shouldn't they know better and socially distance?
I mean, I'm sure they do, but like gravity doesn't take no for an answer.
There's no option, right? I guess galaxies, if they come too close, they will just merge, right?
Well, not necessarily merge. It depends, of course, as well on how fast are the two galaxies going. One of the main types of galaxy interaction, which I suppose is the kind of umbrella term, which you could say mergers come underneath, is just a galaxy flyby, where all it is the galaxies kind of go past each other, wave at each other, maybe distort each other a little bit, and then just continue on their merry way, because they're going fast enough that the gravity doesn't stop them and kind of cause them to begin circling in and merging together.
So the other thing is, and I guess this is related with your work, can we just take like a picture of galaxies undergoing a merger and infer how they looked like before? Can we kind of turn back time?
In a way, yes. But this obviously comes with a whole load of base assumptions and that sort of thing. So what I kind of do at the moment is I will look at an observation of a galaxy, and then I will go to a simulation suite and then start trying to, like, you know, start plugging in different parameters, say the how fast the galaxies are going, the mass ratio, how large they are, the galactic radii, and disk orientations and all that kind of thing. And then what I do is I keep looking at that simulation output, and I keep saying, right, does that look like my observation? And if it does, then I can say within a reasonable assumption that I've kind of recreated that interaction over the course of the last, you know, billion years or however it is. So it's one of those, and sorry, we can also do other checks of it as well, of course, that we can look at the features that are formed, such as those tidal tails, tidal bridges, spiral shapes and whatever. But also we can look at, say, the populations that might form. So if you have a correct interaction, then the starburst will be in your simulation will be the same strength as actually happened in the past, and that sort of thing. So you have lots of kind of little checks that can say, is my simulation accurate to what I'm seeing in my observation? But that still comes with the caveat of most of these simulations start with, I'm assuming I have two disk galaxies coming in and interacting with each other. Now, what happens if one of those wasn't a disk galaxy and had undergone some previous merger and then came in and then interacted again? That's entirely possible, but that's not the base assumption that we really use.
So the other thing is when galaxies go through these big mergers, at the end, will they look very different from galaxies that don't merge at all?
I think it's probably not the most satisfying answer, but it depends. So if you have, as I say, a low mass galaxy, which has just come in and get some sort of like absorbed or something like that, or just distorted by a much larger mass galaxy, then we won't really see that, because that will probably come up as just some satellite of the much more major galaxy. An example of this actually is, I think it's called the Sagittarius Galaxy, which was quite recently discovered, and it's this galaxy that has been orbiting the Milky Way and is getting absolutely annihilated by it, because it's just tiny, and the mass ratio is very much in the Milky Way's favor. So we kind of only discovered it recently because it's been so torn apart. Again, if you have the major mergers, then you will see some long-lasting distortion in the disk, and we'll also, when we look at the galactic spectra, because there's this thing that happens called starburst, which I suppose I should define. It's when, because of the interaction, all of the gas in your galaxy suddenly experiences a load of torques and that kind of thing, and a lot of force on it, so they suddenly will collapse in, and this thing called a starburst happens. Now, regular galaxies, say the Milky Way, is producing about 1.3 solar masses of material per year, like as stars. But in some of these really major mergers, this can reach thousands of solar masses per year, which is just, you know, tons more stars than normal. So then when you looked at a galactic spectra that had undergone something like that, like recently, then you would see like these spikes at different wavelengths, which correspond to much younger or secondary populations of stars that have suddenly all formed at the same time, which can then have an effect on your spectra. So I'd say, to make a long story long, it depends.
And it must be the most common answer in science, I'm sure.
Yeah, unfortunately.
Now, before we take some questions from YouTube, I'd like to introduce Emma. So Emma, thanks for coming back. You were here on episode 0 when we were starting it off. Even worse than now in terms of explosions. And Emma, you just got your MPhil from Lancaster University, but you've been doing research projects, I guess, almost since you were born, because you've been working on the super deep ALMA data, looking for very distant faint galaxies. You've been selected for the LEAPS summer program at Leiden, ESA, and working on globular clusters, but also studying Lyman alpha halos across cosmic time. And you will soon be moving to Groningen to do your PhD with the amazing Amina Elmi, and to work with data from the Gaia satellite, among many other things, which I'm sure you'll tell us all about. Now, your love for globular clusters is absolutely obvious to anyone that has met you. But the important question to begin with is, what exactly is a globular cluster?
Yeah, so a globular cluster is a collection of stars, and these stars are all very old, and these clusters can contain millions of stars that are all gravitationally bound together in a roughly spherical distribution. And these globular clusters are much larger than our own solar system, but much smaller than our actual galaxy, the Milky Way. So within our galaxy, there are around 150 known globular clusters, and all of the stars inside a globular cluster all orbit this common center of gravity of the cluster. And then the cluster itself orbits the galactic center, which is quite amazing, really. And I said that the stars are very old, and the ages of these stars are actually of the order of the age of the universe itself, which is what makes them super exciting and super important, because we can find out more about the universe just by looking at these globular clusters that are in our backyard.
And so we're seeing one of these globular clusters more closer to the bulge.
Mm-hmm.
Do we think that they all formed within our galaxy, or are they kind of weird and maybe they formed elsewhere and we kind of, I don't know, kidnapped them from other galaxies?
Yeah, so a lot of the globular clusters that are surrounding the bulge and in the bulge area of the Milky Way are thought to have formed with the Milky Way itself, but most of the globular clusters in the halo are actually thought to have been accreted from other galaxies. So like David was talking about the mergers of galaxies and how if you have a small merger, like a satellite galaxy, like the Sagittarius Galaxy he was talking about, it can be completely destroyed and completely engulfed into our own galaxy. And we can actually find globular clusters in our galaxy that have the chemical and kinematical properties that suggest that they're from smaller dwarf galaxies, and through the mergers have been accreted into our galaxy. And so the globular clusters, it can be important for learning about our own galaxy's formation, but also about the galaxy's evolution, because we can look at these ones that have come from different satellite galaxies in the past. And also it's thought that maybe during the mergers, globular clusters could actually form. So a new sample of globular clusters could form in our galaxy, because the conditions mimic sort of a starburst sometimes, which can be thought to be the conditions that are needed for globular clusters to form. So there could actually be so many different populations of globular clusters in our galaxy, which would be useful to understand more about the evolution.
And within these clusters of stars, how many stars are we talking about? What's kind of the minimum to maximum number of stars?
So I think like the average is around like 10 to the 6, so like 1 million stars, but probably like 4 or 5 million stars. I think Omega Centauri, which is the largest globular cluster in the Milky Way, has around 10 to the 7 stars. I might be remembering that incorrectly, but it has the most stars anyway. It's the largest cluster in our galaxy, but they all have on the order of a couple million stars.
And the other thing that's important to address is, are these globular clusters still forming in our own galaxy? Are there sites currently where these can form?
So in our own galaxy, the only star clusters that form today are called open star clusters. So these are much younger, a lot less stars in the cluster, and they form, and they aren't as many stars or as gravitationally bound. So they don't last as long. Basically, they disperse out. So they can be found in the disk forming in our galaxy today. But globular clusters aren't found forming. They're all around 12 billion, 13 billion years old, and they all formed in the early universe. And they've actually managed to last bound together in this structure for 13 billion years, which is incredible.
And I think a relevant question, I guess, from YouTube, so I don't ask it, someone else does. Maybe the voice from beyond can read a question from Anna about the typical look-back time.
Yes, so from Anna asks, what is the typical redshift look-back time that we can expect to find globular clusters information?
Thank you for the question. So globular clusters are thought to have formed at redshifts greater than 2. So the range of redshifts in which they're thought to have formed is actually quite large, because we can't accurately measure the age with very small error bars just yet. So it's thought that they could have formed up from like the very beginning of the universe up to redshift 2. And there's a lot of evidence that they formed at high redshifts, such as redshifts 8 to 6, around that time, around what's called the epoch of reionization, which David had a video about a few weeks ago, so you should check that out. But the epoch of reionization is when the universe became reionized, and globular clusters are thought to have been potentially a source that could have contributed to this reionization, because they produce all these emitting UV photons that could help with this reionization. So they are thought to have formed around that redshift, but we can't yet constrain exactly when.
I think we do have another question for Emma, and before we put some questions to David and Rita that I see that we have on YouTube, maybe from Jana Martins.
Yes, so Jana asks Emma, how can we use GCs to estimate dark matter?
Thanks. Yes, so one of the ways that I know of is that globular clusters can be used to calculate the mass of the host galaxy. So the number of globular clusters in a galaxy is thought to correlate with the total mass, and this total mass can be used to kind of determine the dark matter halo mass that's found in our galaxy. I think there are probably other methods, because as far as I'm aware, globular clusters can be used for pretty much everything, but that's the only one that I really know about, so yeah.
And before we move on, I think we also have a few questions for David and Rita. So we can start with the question from João, I think, about any surprising insights.
Yes, João asks, are there any surprising insights you have managed to get with these particular maps, or that you consider the most important so far?
Is that for me? I think so.
Yes.
That's a tricky question to answer, simply because the scope of the science that comes out of these maps is really, really broad. But if I can have my personal bias, I think it's really interesting how things that were once, a dream are now completely commonplace. And so one of the things like that is finding the signature that I talked to you about on this pattern in the distribution of galaxies, which we call BAO, stands for Bionic Acoustic Oscillation. It's actually a signature in a distribution of galaxies that was set up, that formed when the universe was only about 300,000 years old. Okay, so you're looking at something that was really sort of put in place in the early universe, and you see it in the distribution of galaxies today, and you're seeing it incredibly accurately. And so we did this for the first time with SGSS data in 2005. And now that's commonplace, and now everybody uses that to measure the expansion rate of the universe. But 15 years ago, it wasn't a surprise because we were looking for it, but it was incredibly exciting. And now everybody just takes it for granted. So I kind of like that.
It's always like that with science, I guess, right? We take for granted things that a few years ago were magic. And I think for David, we have a question from Jana Martins about the timescales.
Yes, so Jana Martins asks, what is normally the timescale of a merger?
Sure. Thanks for the question, Jana. And just before I answer, thanks for the happy birthdays, everyone. So at the timescale of a merger like that I simulate is like about 0.5 gigayears, probably 1.5 gigayear or billion years, sorry. But then of course you have to take into account there might be multiple passes and that kind of thing, and there's going to be a long, like depending on the angles of your two galaxies or where they're traveling before they kind of start this this gravitational attraction and coming together, there might be like a lot more of an infall time. So I think that like the Milky Way is meant to be merging with Andromeda in some like 1.5 to 2 billion years, but we've been traveling in that direction for ages now. So yeah.
Before we take more questions from YouTube, I'll go back to Rita to ask a few questions more about your exciting research. So apart from working on these surveys and kind of constraining, I guess, the scale of the universe and dark matter, you were also a galactic archaeologist, I would say. So can you explain us a little bit about how we can learn about galaxies, like their history, by looking at their properties in the present? Yeah, so galaxy archaeology was what got me into these surveys, and it's still very close to my heart. And so it's a little bit like, it feels a little bit like magic, but what happens is that
we can look at a galaxy today, and you can look at the stars in that galaxy, and you can simply, well, not simply, it's complicated, but you can measure the ages of these stars. Okay, and so say for example, you find a galaxy that will typically be very large and very red and kind of blobby, and when you look at the ages of the stars in that galaxy, you find that they're all about, I don't know, 8 giga-years old, and this galaxy is at present day, so it's nearby to us. So you can tell immediately that there was a huge star formation event in that galaxy 8 giga-years ago. Okay, so by looking at the distribution of the stars and the properties of the stars, their ages, the metal content, so anything that's in them, there's no hydrogen, of these stars, you can tell an awful lot about, you know, the path that specific unique galaxy took to look like the way it does today. And you can do that by looking at galaxies today, which is what really fascinated me about this at the start.
And I mean, in terms of the practical terms, are you literally an archaeologist? Do you point at galaxies and try to find fossil stars and I don't know, that have died, or do you look at the stars that are still shining to get those signatures?
You mostly look at the stars that are still shining. You can also look, I mean, there will be lots of stars that lived and died. So particularly massive stars, they live fast, they die young. So, you know, but the thing about stars is when you have a burst of star formation, you get an awful lot of low mass stars and then a few high mass stars. And so, and they all, we call this the initial mass function, and they are all born with this sort of distribution. So even though the high mass stars are long gone because they burn through their fuel really quickly and they're gone, you still see the old ones. So you can imagine that, you know, that the young ones also formed and died. And the remnants will be around. Measuring them, detecting them is a different matter, but you can account for them in the models. You can account for their contribution to the total mass of the galaxy because you see the old stars. You see the low mass stars that are still there. So
those are essentially the fossils, are the things that live much longer.
Yeah.
And for the research you've done since you became I guess a galactic archaeologist, to making maps of the universe and trying to learn more about, I guess, what we would say cosmology, in your personal view, what is like the coolest or neatest result that you think you got? Either, I mean, it's always a teamwork, obviously, but what is it, and could you share it a little bit with us?
You mean from my research on this?
Yes.
So what I sort of thought was really neat, and I think it's becoming clearer now that we have lots and lots of data, is that from this fossil record of the galaxies, okay, by trying to disentangle how a galaxy formed, you can also have a glimpse of how the dark matter halo that hosts that galaxy formed. Okay, and that's, for many of us, that's sort of the holy grail. Okay, we don't see halos, dark matter halos that embed the galaxies. It's really hard we can't do a fossil record on the halo formation history because you can see the dark matter particles. But it turns out that actually that formation history of the halo is somehow imprinted on the star formation histories and the properties of the galaxies today. And so, so that's one of the things that I think I'm starting to really believe now myself, even though I've published more than one paper on this. I'm now actually starting to convince myself this is really happening. This is really true. We can really see, you know, start to disentangle how the halos form by looking at this fossil record, which I think is really exciting.
So is that one of the major things you're working on at the moment that you're excited about?
At the moment, yeah. So that's right. So at the moment, I'm really interested in sort of trying to understand how structure and halos form, acknowledging that we can't actually see them, but we can see the galaxies. And actually, there's an awful lot of other properties of the galaxies that are entirely determined by the growth of the halos themselves.
And the other thing that's always good to know for people that might be interested in your field, is there something that people should definitely get excited? I mean, we just got the largest, most detailed 3D map of the universe. Is it going to get better, and which kind of telescopes might do it?
There's always better, bigger, and more in astronomy. That's you know, I can't see a time when that doesn't happen. So yes, so the main answer to your question is yes, there is. So the one that I'm personally involved in is called DESI, which is Dark Energy Spectroscopic Instrument, which is a little bit like SDSS on steroids, right? So it's going to go deeper and wider and larger. Is operating, well, not now, but it started operating just before lockdown, operating from a larger telescope. But I think what's really interesting is also start combining data sets. So this DESI map is going to be much more detailed than an RCSS map, but you can also combine it with other maps that we have, for example, of integral field spectroscopy that tell us not just about the properties of the stars, but also how the stars are moving within a galaxy. And so you can start combining the way things move within a galaxy to where the galaxy is and the properties, and trying to link that with the history of the halo, which is something that I'm personally really, really excited about.
So there's lots of new things still coming. So even though it's brilliant, it will always get better. It's very good. And David, so you told us that you kind of use some simulations and then you compare it with real data. So what kind of data and telescopes do you actually use or have been using?
Well, at the moment, I'm mainly using SDSS data, which is really has all the color magnitude data and and you can easily look at anything you found on there on the NED. It's the NASA Extragalactic Database in order to get the redshift information. So that I don't really use any telescopes. I just piggyback off of other people who've used the telescopes, and then try to recreate what they see in my simulations.
And in practice, what is like your main research question that you're trying to address? You already covered it a little bit, but could you explain it a little bit more?
Well, I guess the research question I'm trying to address is how do we get sort of these tidal features from a merger? So throughout the questions I've answered, I've talked about the mass ratio of the two galaxies, or the radii of the galaxies, and like the disk orientations and the impact parameter and all that kind of thing. And the question I kind of want to ask is, what set of those numbers do you kind of need, which makes say a tidal bridge forming more likely, or a tidal tail forming more likely, or I don't know, like the complete destruction of both disks into like something like the antenna? Like, what set of parameters makes that most likely? Now, to do that, we're having to do a whole load of statistic stuff in order to do a big search of parameters these things are called parameters, and I'm doing a big search of parameter space to find which ones are more accurate or give you that higher probability of forming these features. And the reason for this is these features are often very faint. They can lie in what's called the low surface brightness regime, and that's a regime where these features will have a brightness of less than 27.5 magnitudes per arc second. And remember, the higher the number is, the dimmer that is, the dimmer that feature is. Sorry. And telescopes kind of have only recently started to be able to kind of really get down to that low level of surface brightness. So, and this problem kind of won't really be solved fully until we get the Large Synoptic Sky Survey Telescope out, or LSST, up and running, which will do this huge survey, which should actually be able to finally get into that low surface brightness regime. But for now, I kind of want to say, my parameters, or my parameter search thing has revealed that observation there should have a lot more features in it. Won't that be interesting to look at when these telescopes, which should hopefully be able to see them, kind of come online?
So do you worry that when the data gets too good, your models just keep up?
Well, thankfully there is sort of a secondary use for this model, which is when the data does get too good, it should be able to take any observation that you have, and you can feed it into the algorithm, and then it will just cycle through all the parameters, and it will find, here are the parameters that best match that observation. Keep spitting out simulation images. And it will then say, this simulation image looks most like my observation image, so therefore we can assume the underlying parameters are this of the interaction. So thankfully I won't be out of a job when the LSST comes online.
It's quite the opposite, right? The more the problem, the principle, the more things we have to find out. Emma, coming back a little bit to these globular clusters, and we already had a question about kind of how far back do we need to go in principle to find them forming? Now, do we have candidates already for actual observations where we might have found some of these globular clusters?
Yeah, so there's a few studies that have found some of these potentially young globular clusters at high redshifts around 6 and 7. But the issue is because they're super faint and super small compared to galaxies, they're even harder to find. And currently they've been found using what's called gravitational lensing. So this is where there is a supermassive source in the way of a small, like potential young globular cluster or star cluster. And the big source, like maybe a galaxy cluster, magnifies the object that's behind it. So we can see things like star clusters at redshift 6 when they've been magnified. So a few studies have found these gravitationally lensed sources that they've reconstructed and they believe are young globular clusters because their properties match what we expect. But the issue is we don't actually know exactly what properties we expect yet, because it's hard to model all of the different parameters that change in a globular cluster over time. So there are loads of different ways in which clusters can lose their mass. So there are stellar evolutionary processes and there are dynamical processes and all sorts of these processes that we can't model perfectly just yet. So finding these young globular clusters at high redshift and kind of improving on these models and figuring out how they go from what they look like in the early universe to what they look like in the Milky Way today will be vital for furthering that field.
So one of the things you did in your research was kind of take the opposite approach, right? So it was to study the globular clusters in the Milky Way to get their properties and then turn back time. And in your research, so are they really bright enough for us to see them today or not?
So in my research, if you had no gravitational lensing and you were just looking at a star cluster at high redshift with the Hubble Space Telescope today, they wouldn't be bright enough, according to what I calculated. But there was a lot of assumptions that were used in my master's project. So I said before that there are stellar evolutionary processes and dynamical processes that decide how much mass a cluster loses over its lifetime. So when I was backwards modeling that and going from a cluster today to a cluster at high redshift, which would be more massive, I only accounted for the stellar evolutionary processes because the dynamical is too hard to model at the moment and way above my master's project anyway. So what I found was that they are too faint because they weren't quite massive enough to be observable with Hubble, but they would be observable with James Webb Space Telescope, JWST. So when that launches, that would be really great because we'll be able to hopefully observe these. And because my assumptions that were used, they would actually be probably just about massive enough to maybe just be observable with Hubble today. But it depends on the redshift that they formed, and because we don't quite know exactly where that is, if they formed at the higher redshifts, then we will need James Webb.
I guess when it get launched, it was just delayed yet again. That's the story of our lives as astronomers with James Webb. Now, in your PhD, I assume you will not be relying on JWST, which is a great idea. Can you tell us a little bit about what you will be investigating for people that might want to get excited about the field?
Yeah, so for my PhD, I'm not focusing as much on globular clusters as I have been doing at the moment. So I'm going slightly further afield and looking just at the Milky Way and looking at using Gaia data. So that is a space telescope that measures the positions and the parallaxes and of all the stars, or at least as many stars as we can get in the Milky Way. And so what I want to do is kind of disentangle the stars that are in the halo, so we can figure out using the chemistry and the orbital properties whether those stars formed with our galaxy or whether those stars are from a satellite galaxy or a dwarf galaxy that merged with the Milky Way in the past. And then we can kind of form like a merger tree of how the Milky Way formed itself. So all these small galaxies that have formed together and grown together to form the Milky Way that we see today. And it's super cool that using telescopes today, and just looking in the Milky Way, we can actually figure all that out. So hopefully it'll work out.
Another kind of galactic archaeology, and now done with Gaia. That's really pretty cool.
Yeah.
Before we finish, I always like to tell our audience and know a little bit more about who you are and your paths. Right? So I'll start with Rita. I know she may not have the most clarifying answers for some of the questions, but we'll start with kind of the favorite telescopes that, I don't know, might be the ones you've used or the telescope you would love to use at some point. Rita, do you have a favorite telescope?
Yeah, I'm just going to have to say the Sloan telescope, because it really is a little telescope that it never, it doesn't stop, it keeps on going. And just from pure resilience, I'm going to go with that.
I mean, I particularly love the INT, which is also a 2.5 meter telescope that really stands on the shoulders of giants sometimes. Yeah. David, do you have a favorite telescope?
I mean, I think I've got to be very generic, and it's got to be Hubble. Being able to like look at all those high resolution amazing pictures like when you're like 14, 15 does a lot to inspire you to keep going with astronomy, even if like the wee telescope you have in your back garden isn't really giving you the same thing, isn't showing you the same images. So yeah, it would have to be Hubble.
And people watching, of course, feel free to tell us what is your favorite telescope as well, to see if it's that different from our guests. Emma, do you have a favorite telescope?
So since you stole the INT and David stole Hubble, I guess I'd have to say Gaia. So I've never actually worked with any Gaia data yet, but I'm super excited to work with it. And it's incredible how much it's like revolutionizing the field of studying the Milky Way and all fields, but especially that I'm interested in. And yeah, I'm looking forward to looking into that.
And in terms of like astronomers in the field, either people currently working or historical figures, do you have a favorite astronomer? I'll start with you, Emma.
So I think I spoke in the last one I did about Dr. Maggie Adarin-Pocock, because she was doing some work. Well, she did a talk when I was in year 11 at school about colonizing Mars, which is what made me super excited about astrophysics and astronomy and space. But I guess if I was to go for a favorite astronomer at the moment in astrophysics and in my field, I was super inspired, and my passion for globular clusters came from working on an internship with Alice Zocchi, who works at ESTEC ESA in Leiden at the moment. And she just has so much passion and enthusiasm for globular clusters that she passed it on to me. So, and she taught me so much, and she was super patient with me while I learned how to code and everything. So she's really, really inspired me to like study those things and keep going.
And David, any favorite astronomer?
Yeah, again, the field that I worked in, way back when I just finished, I say way back, I'm not that old, but way back when I finished first year of university, or maybe second year, I actually managed to land an internship in Warsaw, where I got to go and work on, actually it was, I think it was galaxy interaction to do with bar, like the formation of bars. But the professor who took me on was someone called Eva Wakas, I believe. And yeah, no, she was just really cool. She, guided me through the entire project and basically was the reason I was just testing the waters. Like, I was research for me, and I went, you know what? Yeah, this is it. Yeah, this is pretty good. So yeah, definitely are.
And Rita, any favorite astronomer?
So I don't have a favorite astronomer, but I was listening to David and Emma, and they were saying who inspires them, and I can tell you who inspires me now, and that's my students. Okay, so hands down, the people who keep me going through endless teaching and admin, and the really hard times of academia, is seeing the passion of my students, how they bring in really interesting perspectives in what they do, and so I really don't think I could do this without them. So they're there for me. So
yeah, definitely agree. And the final question I have for all of you is to do with your path so far, and whether from a young age you already knew that you wanted to be an astronomer, or whether that kind of happened, as for many astronomers does. And Rita, was it something that you dreamt of already as a child, or did it happen much later?
No, I decided I wanted to be an astronomer when I was 13. That was it. And yeah, I was reading Cosmos by Carl Sagan, and that was kind of it. Really boring story.
And the path to, I guess, becoming a professional astrophysicist, I guess it was relatively smooth. Were there, stages at which things got more complicated? In case you want to share anything with people watching us.
So I think, well, I was incredibly privileged. Okay, I had parents who could support me. So when I started my undergraduate degree, so I did, in Portugal, you sort of decide where you want to study high school when you're about 15. I wanted to do physics, and then I went to do astronomy in Portugal, and then I really wanted to move out of Portugal and go to Edinburgh, and I was incredibly privileged, and my parents could just financially help me do that. So that was just pure luck from where I came, where I was born in this world. And then from then on, I do think it was kind of luck, because I had a fantastic PhD supervisor who, really sort of spurred me on. And then I had a fantastic postdoc mentor who would not let me stop until I applied for fellowships that I did not want to apply for. And it was that led me to land a fellowship, and that led to a permanent position. So, I think there was a lot of luck in the people that got involved in my path, both my parents and also my mentor. So yes, I wanted to be, but I think a lot of it was sheer luck, and I'm very thankful for it.
And a lot of hard work, but yeah, I guess I'm sure. And David,
I think I'm kind of the same actually. Like, I got my first telescope at like 8, and then pretty much was wanting to be an astronomer from then. I think the only thing I remember wanting to be before that was a bat. So like, it's just always been that. And then again, it's I've been very lucky with the people who've kind of inspired me, I guess, with to keep the astronomy going. When I was like 11, 12 and stuff, I used to have a biology teacher that would just tell about like all my observing time and stuff, and that really just kept me into it, like kept me into astronomy all the way like through being a teenager and stuff. But then when it like came to uni and stuff, it was the same luck and privilege that Rita was talking about. I had to get the experience in order to look good to go do a PhD. I had to go and do internships and stuff, and they were not well paid. And if I wasn't in the lucky position that I was, then I wouldn't have been able to do them. Yeah, just always wanted to be in the path. I got the PhD, and now I'm kind of like, well, I'm doing a PhD. What do I do now? PhD in astrophysics. It's the end goal.
And Emma, I guess,
Yeah. So I originally, I didn't really know much about space or galaxies or anything as a child, obviously, but I didn't really find the interest for that until I was probably around 16. When I heard this talk about colonizing Mars, and I thought it was super cool, and I was like, oh, I want to go to space, I want to do all that. And then I had a physics teacher at school and for my A-levels as well, who was super encouraging and super believed in me when I used to think that I couldn't do physics, and that really, really helped. And so I applied to do physics at university, and still didn't really have that confidence. I remember first year being a bit not as confident as other people, and feeling that I didn't really quite belong. And then in the summer at the end of my first year, I did my first internship with David Sobral at Lancaster, and it was incredible. I didn't know what was going on half the time. I didn't know fully how to code, but I learned on the job, and I had such a good time. And then ever since, I've just known that I wanted to do research, and I've been lucky enough to be able to do a few different internships, and again had the same privilege to be able to go to these places and learn these things, and just keep going with the research and see where it takes me.
It's really interesting, because usually there's always half the guests I guess went on to astronomy even later. I guess on average, you were still a child when you decided. Emma was a little bit later. But I think it's also common, the importance of mentors and I guess people helping us, especially at the right times when we feel like we want to give up. And I think people should know that those times will always come regardless of what you pick, and be aware of that. So I think this is a good time to finish. Essentially, that's all we have time for today. Thank you so much again, Rita, David, Emma, and the voice from Beyond who took the questions live from YouTube. And happy birthday again to you, David.
Thank you.
So it was really brilliant to have you, and let's have a final round of applause for you all. So thanks to everyone who watched, participated, and asked questions. We will be back one more time next week at 5:30 UK time for the season finale of The Earth is Flat on Planet Pluto, where we'll be talking about the CR7 Galaxy that's just sitting next to me, and also about other super bright galaxies that have been discovered in the last 5 years since CR7 was discovered. We'll talk about what we've learned, which other super bright galaxies we've discovered, and what are the current open mysteries about CR7 and other galaxies. Joining us will have the amazing Jorrit Matthei, Sergio Santos, and Heather Wade. And everyone is invited to join us, as we will also show how we discovered these distant galaxies live. So this has everything to go wrong, and anyone can do it at home and then post the coordinates of the galaxies that they found. And this obviously includes even Cristiano Ronaldo. If he wants, he can join us as well, along with his kids. It will be super fun to discover and study distant galaxies, and everyone can learn how to do it in simple steps. So it's really going to be awesome. And until then, don't forget that you can subscribe to our YouTube channel right there. And also you can watch previous episodes on our YouTube channel, and check out the entire program at xgal.uk. And if you speak Portuguese, you can also watch our Portuguese version Saturdays at 9 p.m. UK time. So until then, keep looking up, and see you next week, everyone.
Liftoff of mission 41D, the first flight of the orbiter Discovery, and the shuttle has cleared the tower. Welcome home, Columbia. Beautiful, beautiful.
You want us to take it up the hangar, Joe?
We're going to dust it off first.
3, 2, 1, 0, and liftoff. Liftoff. Americans return to space as Discovery clears the tower.
Roger roll, Atlantis.